when we say that the limit of a function as x approaches a number is L, L being a number, which means the limit exists. This says the limit exists. I have a few things to identify or clarify if you want. Is x equal to a? No. Very good. That's one thing that you have to remember. When we say x approaches a, we really mean it. Approaches a, not equal to a. Okay. Perfect. Now, one other thing that I would like you to be clear on is when we say that the limit exists, we mean this side approaches L, let's say 10. This side approaches 10, and this side approaches 10, which means the right-hand limit is, and the left-hand limit is the function defined there? Not necessarily. It may or may not. So these are the other two things that I would like us to put in writing. So when we write that the limit of f of x as x approaches a from either side is L, we mean two things. We mean that the limit of f of x as x approaches a from the left is L. And we mean that the limit of f of x as x approaches a from the right is also L. And another note here, note, the function does not have to be defined at a. The function f of x does not have to be defined or exist to be defined at x equals a. The limit to exist does not require the function to exist at that point. Perfect. Now, moving forward, there is a very important function that we are going to look at. So I do not want to wait till we can prove this other than graphically. So for now, we're going to prove it graphically. So let's find the limit of sine x divided by x as x approaches 0. Limit of sine x over x as x approaches 0 from either side. What do we have to do whenever we are asked to calculate a limit? What is the first thought? Although I just wrote it here, I have to plug it in. Why? And before I continue, I have another document for you that I created some time ago, and every now and then I add to it. Okay? I want to say complete. If we find something that it's not in here, we will add it in. This is a list of all the limits that we will see this semester. It's a big document. It's long, and it has a lot of different limits. And we will go through all of them. Let me know if I counted correctly. 7 and 7, or maybe 8. Okay, so yes, we will plug in, and what do we get at the top? 0 over 0. Very good. So there is a chance that this limit exists because it's 0 over 0. If it were 5 over 0, we knew from the very beginning that it would have not have any chance. So now let's take a look at the graphing calculator. We cannot prove this just yet. We will very soon. And not with a graph, or it's not going to be a need for graphing. So let's go to make sure that the mode, your mode has to be in radians. Unless 99.99%, 99.99%, unless there is something that when we'll discuss it. Okay, make sure that the mode is in radians. Then go to y equals. and plug in function sine x in parentheses divided by x. Since the limit is determined when x approaches 0, I don't care to see anything else but what happens around 0. So I'm going to create a viewing window that helps me with that. So in window, I'll go to -1 to 1. With a scale of 1, it's fine. And from -1, let me put -2. -2 to 2 with a scale of 1. And I'm going to graph it. Okay. First question. Do you think this function is defined at 0? Absolutely not. There is 0 in the denominator. It cannot be defined at 0. However, can anyone guess the limit of sine x over x when x approaches 0 from either side? Exactly 1. The limit is 1. It happens that, and you can verify that if you want, that the limit as x approaches 0 from x over sine x is also 1. So you have these limits. I presented them up here on page 3 of the summary handout for chapter 2. And we're going to work on this problem right now, but not before I explain what I mean by this. Okay. Now, in general, what we have to understand about this function is that if, why did I put my markers right there in the way? I don't know. Say it again.
Why would it be 1?
The limit?
Yes.
Okay. So when x is here, I have this. When x is here, I have this. When x is here, I have this. When x is here, I have 1. Right? Yes. Right? So both sides, the function values approach 1. So I had 0 to 2, and this was 1. Is that better?
Yes.
Perfect. Okay, so do not cross it out like that. I'm just trying to make a point. This is supposed to be understood in this way. Limit of whatever approaching 0 from sine of whatever over whatever will always be 1. What am I saying here is these 3 pieces have to be identical, and this number has to be 0. So what I'm saying is that if I choose to have in this spot x minus 3, then I have to have here x minus 3, and I have to have here x minus 3 for the answer to be 1. If any of these is not x minus 3, the answer is not 1. But we never really write x minus 3 approaches 0. But what? What do we write? If we don't write x minus 3 approaches 0, we write x approaches. Just move it to the other side. X approaches. When we move from one side to the other. Exactly. So every time x minus 3 approaches 0, it means x must approach 3, because only 3 minus 3 will approach 0, right? Or you just consider that you move -3 to the other side by changing its sign. So let's look at an example now. Any questions? Any questions? Okay, so I have an example here on our handout. So this is limit as x plus 2 approaches 0, sine x plus 2 divided by 2x plus 4. As long as I make these 3 pieces the same, as long as they can be the same, then I will write that the answer is what? 1. But I can't write it, right? This is basically x approaching what? Indeed. This is okay, but this one is not. What will you do? What is the only thing we can do to 2x plus 4? Indeed. So then I will rewrite the whole limit as x approaches -2 from sine x plus 2 over twice x plus 2. Now I do have 3 pieces, the required pieces the same. This, because it means x plus 2 approaches 0, so it's this. I have this, and I have this. Can anyone give us the limit? Perfect. So the limit of sine x plus 2 over x plus 2 approaches 1. But 1 times 1/2 will be 1/2, indeed. Any questions? Yes?
Why are you only plugging the 2 on the bottom and not the top?
This limit approaches 1 because it's the situation. Limit of x plus 2 approaches 0, sine x plus 2 over x plus 2, which is 1. It's just that I have an additional factor of 1/2 in front of the function. Since this whole thing approaches 1 times 1/2 will be 1/2. Is that okay? Is that what your question was? Yes, please. Vanessa?
So 1/2 the limit?
The whole thing, yes. Because all this is 1, but there is a 1/2.
So 1/2 is the limit?
Yes, because this is 1.
Okay.
This approaches 1, and 1 times 1/2 will be 1/2.
Okay.
And that will be the final answer. Is that clear? Everyone? Yes? Please.
Why did you change the x plus 2 equals 0 underneath the limit?
Into, because we don't write this. We write this.
No, below that.
To show that these 3 pieces are all the same.
Oh, okay.
If those 3 pieces are not the same, I cannot write 1.
Okay.
So just to show that this quantity, and this quantity are all the same, therefore the limit is 1.
Okay.
Because if I have here x plus 3, the limit will not be 1. Or if there is any change, these 3 have to be the same in order for the limit to be 1. Any questions on this? Any questions? Okay, so just please keep this in mind. Sine x over x, or x over sine x, and the pattern. We're going to encounter this again several times this semester. Okay, we can move on now to 2.3, limit laws. There's a long list of limit laws. Actually, there are 11, and we can even produce more, pretty much, but basic ones, 11 limit laws. Requirement. Without which limit laws cannot be applied, or they don't exist, in other words, for us. If those two requirements are not fulfilled. So the limit of f of x as x approaches a must exist. When we write L, it means it's a number. It exists. And limit of g of x as x approaches a is another number m, or it can be the same, it doesn't matter. But it means that the limits of f and g exist. Okay, so let's list at least a few and work with them. Here's the first one. Limit of f plus g when x approaches a. What do you think this will equal to? Just a wild guess.
Be limit of f plus limit of g.
Of course. Limit of f as x approaches a plus limit of g as x approaches a. Since they both exist, the answer will be L plus m. Let's condense them a little bit. What if I have a difference between these two? What will I write here?
Limit of f minus limit of g.
That's it. So we wrote 2 in 1. Here is a second limit that we just used without even knowing that it exists. It existed. So limit as x approaches a from a constant c times f, a function. What do you think this equals to? C can go outside the limit times limit of f as x approaches a. Did we just use this? Yes. Let's go back for a moment. Without even telling you, we used it. We moved 1/2 in front. So I could have written here 1/2 limit as x approaches -2 from sine x plus 2 over x plus 2. This is 1 times 1/2, which is 1/2. So we used a limit law that was simply common sense. Okay? So we could have put 1/2 in front of the limit operator. 1/2 limit sine of x over 2 over x over 2 is 1/2. Because this is 1 times 1/2 is 1/2. Better? Yes? Okay, next one. Again, let me give you a counterexample here. The limit laws can be applied only if this is fulfilled. If this is not fulfilled, the limit law cannot be applied. Okay, here's an example and a counterexample. So limit as x approaches 2 from 1/2 x minus x squared. This is a function f. This is a function g. So therefore, I can write limit as x approaches 2 from 1/2 x, and then minus limit as x approaches 2 from either side from x squared. Can I apply the limit law? Only if this limit exists and if this limit exists. Otherwise, I can't. What is the limit of the first one? Right? When x approaches 2 from either side, the function will approach 2 times 1/2, 1, minus as x approaches 2 from either side, where will x squared go? 4. So how much is 1 minus 4? -3. We were able to apply the limit law because this limit exists and is this number, and this limit exists and is this number. Otherwise, we can't. Let me give you another example. Let's say limit as x approaches 0 from 1 over x minus 3x. You could say, or let's put plus this time. Let's try the sum. You could say, oh, that's easy. Limit as x approaches 0 from either side from 1 over x plus limit as x approaches 0 from either side from 3x. However, you can't. Why? Why is the limit law not applicable in this case? Exactly. Because the limit when x approaches 0 of 1 over x is d and e. Indeed. How do we know that? We graphed this function last time. Maybe, maybe not. Let's graph it again. I just want to make sure. I don't remember now if I graphed it. But in order to be safe, let's graph it. So this is the graph of 1 over x. I think we did it, but let's do it again. So what is the limit of 1 over x as x approaches 0 from either side? Right. Why it does not exist? Because the limit from the right is, and the limit from the left is, therefore it does not exist. Therefore, coming back here, we cannot determine this limit using the limit law. Not allowed, because it's not applicable. Why it's not applicable? Because this requirement is not fulfilled. One or the other or both does not have a limit. Okay? Very good. Next limit law. Which number am I at? I'm 3, right? Okay. Limit of f times g when x approaches a. What does this equal to? Common sense so far. Limit f as x approaches a multiplied by
limit of G.
limit of g as x approaches a. 4. I ran out of room, and no one is surprised by that. So let me go to the next page. Because sometimes when I scan, the bottom of the page doesn't appear. Okay, 4. Limit of f divided by g as x approaches a. This equals, indeed, yes. However, this limit comes with a big if. How come? Why?
Limit of G cannot be 0.
Exactly. So, of course, I didn't write here, so please write it. So it's L multiplied by M, obviously. Here, the answer will be L divided by M, but obviously only if limit of G when x approaches A is not 0, or M is not 0. Otherwise, we cannot apply the limit law. 5. Let's look at limit of the square root of a function as x approaches a, of function f, as x approaches a. What will you say? And I want to emphasize something extremely important here. I could have emphasized it on other limit laws, but this is the first one that is very important. So, what can you say about this? What will you write?
Limit of square root.
Let's say it again.
Limit square root f.
The square root of the limit of f as x approaches a, which will be the square root of L. Big note here. Something for your notebook, something to look forward to, because this is very important. It's a big note. How did we call this? We called it an operator. How do we call this? Exactly, another operator. Can anyone tell us what really happened here? What did I do with these two operators? I literally, either you can say interchange them or swap them. That's exactly what I did. The inside operator became the outer operator, and the outer operator became the inner operator. This is a theorem that we will be looking at further down the road. Swapping of the operators. It's not called the swapping of the operators, of course, but I just want to put a note in here so we can refer back to it when we get to this theorem, okay? Under certain, not always possible, but under certain conditions that we will discuss down the road, conditions, they're conditions of continuity for composition, function composition. So under certain conditions, the swapping of the operators is allowed, or swapping the limit operator with square root or natural log or etc. operator is allowed. Under certain conditions, comma, swapping limit operator with a square root operator, a natural log operator, or other operators is allowed. Or operators is allowed, okay? So this is a theorem that will come into play a little bit later. We will use it a lot. Okay, let's look at another. The limit, number 6, limit of x as x approaches a. What do you think? When x approaches a. A, indeed. A. Very good. 7. Limit as x approaches a from a constant c. What do you think that answer would be?
AC.
Of course. Who cares where x is going? C is still c. No one can change that. Next one. Limit of x to power n as x approaches a. What do you think this is?
Pull the n out.
Exactly. So it's again a swapping of the two operators. It's this. The operator power n was inside, touching x, and now it's outside, touching the limit. What is the limit inside? How much? L, right? This limit, you're right, it's x. It's a. You're right. A to the n. I got carried away. This is not the function. It's simply x. I was thinking of the function for a moment. Thank you. Thank you. Very good. Okay, I think we have enough for now. I would like to practice some limits on page 107. Back to the handout that I just gave out. The handout with limits. Let's, we will be working on this for a long time. This is not going to happen in one session. Okay, this is the limit document. So here's the first one that I would like to work on. And then we'll check each and every one of them as we go along. So some limits can be determined by factoring. Okay? So let's start with that. Limit, and then we can choose other problems from your book. X squared plus x minus 6 divided by x minus 2. What is the first thing we need to do when we calculate a limit?
Plug it in.
Yes, we have to plug it in. Excellent. Good. Just was looking at my video. Okay, so let's plug it in. What do we get?
0.
Ah, that's nice. Bless you. If it's 0 over 0, what do I know immediately?
There's hope.
Exactly. First of all, that there is hope. Secondly, that we can factor. And both top and bottom have a specific factor in there. Indeed, x minus 2. Very good. Limit, so x minus 2 over x minus 2 as x approaches 2. I can immediately find out what that is. Very good. It is x plus 3. We are allowed to simplify because x is never 2. 1 and 1. So the simplified form is this. We can write a theorem right this moment. After you give me this answer, we can write a theorem. Yes, please, Vanessa.
So I'm confused how the one you just wrote, why it wouldn't be x minus, or x minus 2, and you did x.
From last time, from the remainder theorem and the factor theorem. If when I plug in a polynomial a number and I get 0, x minus that number must be a factor. So I plugged in 2 top and bottom, so x minus 2 must, and I got 0. That's why x minus 2 must be a factor of the top and the bottom. So, and then the numerator has an extra factor of x plus 3. Okay, so after you give me the answer, we are going to write a theorem. What is the answer on this? You can split it into two limits. The limit of x when x is 2, and we know what that is, plus the limit of 3 when x approaches 2. What would be the answer? The limit of x when x approaches 2 is, right? So we just wrote that a minute ago. The limit of x when x approaches 2 is 2. So this is 2 plus 3. So the limit is 5. So here's a theorem moving forward. Oh, I'm swallowing letters today. So theorem. The limit of a polynomial Sx approaches A is, so this is specifically a polynomial. Any degree you want, first, second, third, 1500. The limit of a polynomial when x approaches A is?
A.
What did we do here? This is a polynomial. How did we get 5? What did we do to this polynomial to get 5? Right, so what do I get then? So we plugged it in. So just tell me what to write for any polynomial. Exactly, thank you. Thank you, Chris. Of course. Of course. In other words, in order to find the limit of a polynomial, I am legitimately allowed to plug it in. It's legitimate to do it, although I keep saying x cannot be a. But for a polynomial, in order to determine the limit, I'm allowed to do so. Okay, so this is the theorem. We have one more for rational functions. So another theorem, limit Sx approaches A from P of x over Q of x, which means a rational function. What do you think this will equal to? Of course, if there is an if here. Yes? If what? Yes. If Q of A is not 0. Exactly. So we have a similar theorem for rational functions. In other words, if this little number, A, is in the domain of the rational function, legitimately plug it in. If it's not, you can't. That's all it means. So moving forward, every time we calculated a limit of a polynomial, we can write the answer right away by plugging it in. When we are determining the limit of a rational function, we can immediately plug it in as long as this number is in the domain of this function, if the function exists at that point. Okay, so we can consider the factoring situation done. Okay, let's move on with a couple of examples from your book. I would like to look at problem, let's say 20. On page 107. Any questions? Please stop me. Any questions? 107. And we have limits. T to the 4th minus 1 over t to the 3rd minus 1 as t approaches 1. Okay, so let's plug it in, because we don't know what this is. When we plug it in, we get?
0.
Okay, so your guess is as good as mine. I have no idea what we are going to come up with. Hopefully, a number that is not, that exists. In other words, not infinity or negative infinity or DNE. So for now, what will I already conclude? I plugged in 1, so there must be a factor of
T minus 1.
and t minus 1 in the denominator. Awesome. However, I'm not there yet, right? So let's start with the numerator. How do I factor the numerator? So this is a difference of squares. How do I factor the difference of squares?
T squared minus 1.
T squared minus 1 and t squared plus 1. Very good. Now, how do I factor the difference of, this is not the difference of squares, but the difference of cubes. Very good.
A minus B.
Right, so t minus 1.
A squared plus AB plus B squared.
Excellent. T squared minus plus 1 times t plus 1. Okay, one more step. This is not factorable. This is not factorable. This is not factorable, but this one is. How do I factor t squared minus 1?
T plus 1, T minus 1.
T plus 1, very good, times t minus 1, t squared plus 1, over t minus 1, t squared plus t plus 1. What did we say that we expected to happen for sure? Because we got 0 over 0? There is a factor of t minus 1 at the top, and there is a factor of t minus 1 at the bottom. Do we see them? Once I remove this factor, and there is no other factor of t minus 1, the problem is gone. So as long as I can remove the t minus 1, at least the one from the denominator, of course with one from the numerator, then the limit will exist. So then now, this is a rational function that has 1 in its denominator, it's in its domain. 1 right now is not a number that is not in the domain of this new function. So it's a rational function. I can plug it in and I'm done. There is no more 0 over 0. If the top is 0, it's fine, but there is no 0 in the denominator anymore because now 1 is in the domain of this new function. So the top is 1 plus 1, 1 plus 1, 1, 1, 1. So what do we have at the top? Good. What do we have in the denominator? That's it. Could you have guessed from the beginning that 0 over 0 eventually turned into 4 over 3? No, of course not. Any questions? Yes, please.
How did you factor t cubed minus 1?
Yes, it's the difference of cubes formula. A to the third minus b to the third, which is a minus b, a squared plus ab plus b squared. It should be in a front cover or back cover of your book. And we can talk about it more if you want later. I mean, so if this is positive, then this will be negative. So if we are factoring the difference of cubes, then the binomial has the difference and the trinomial has the sum. If we factor the sum of cubes, then the binomial has to have the sum, but in the middle, minus. Otherwise, terms will not cancel out. So this is what we used for a t cubed minus 1. We used t cubed minus 1, t minus 1, t squared plus t plus 1. Any questions? Any questions? Okay, I would like to go to one limit here. So this was done. I would like to go to one limit, which is this. What will you say about limits from sine x over x when x approaches 0? 1. Very good. So please remember that moving on, moving forward. Okay. We also know this limit already. Limit as x approaches 0 from 1 over x, we know the answer. Very good. DNE. I would like to look at number 9. So we have limit as t approaches 0, 1 over t, the square root of 1 plus t minus 1 over t. I copied this problem, I'm sure, from your book. I can't seem to find it right this moment. Yes, it's problem 29. Problem 29 on page 107. So here's what I would like to do. Please don't write it. I would like to write this. Limit of 1 over t, the square root of 1 plus t, as t approaches 0, minus limit of 1 over t as t approaches 0. I apply the limit law that says the limit of a difference of functions is the difference of the limits. Is this okay? Do you agree with this? Why you don't agree with it? Not even the first one. So the limits do not exist. I'm not allowed to apply the limit law because the limit of this is DNE, the limit of this is DNE. Perfect. So then there must be something else I need to do. Can you suggest anything? What is the only thing you can think of? Any only idea that comes to mind that is applicable here? I see two fractions, and I see a difference. What could be the next step? Find the least common denominator, right? What is the least common denominator? Very good indeed. T times the square root of 1 plus t. Excellent. So now I need adjustments for the tops of those two. What does the first one need? Careful. Nothing or 1. What does the second one need? Indeed, the square root of 1 plus t. Can anyone give us the numerator now? Yes? Yes? Do you all agree with this step? Okay. Now I will plug it in. There was no point in plugging in before because I didn't have anything. It was a number over 0. Okay, so then let's plug in now and see what this is. When we plug in 0, 1 plus 0 is 0. The square root of 1 is 1. 1 minus 1 is? Good. And the denominator? Good. Now, it's 0 over 0. Just remember, this is not a polynomial. The numerator is not a polynomial. The denominator is not a polynomial. So let's take a look and see and think of what we can do here. What type of function is it? Yes, it's a ratio. It's a combination of a rational function with something else. Right. So we had something like this before in which we determined the difference quotient. This is not a difference quotient, but we applied a procedure that I would like you to think of right now. What procedure would that be?
Rationalize.
Excellent. Which quantity, top or bottom?
It's the bottom.
Not the bottom in this case. Exactly. 1 minus the square root. That's what we want. Here's why. When we plugged in t equals 0, 0 for t, we got 0 over 0. So obviously, which factor is the problem? Once I get 0 over 0 when I plug in or replace t by 0, which factor I would like it to go away? The factor that creates 0. Which factor creates 0? T alone. T. Well, I have it here. I don't need to rationalize this part. This is not a problem. See, when I plug in 0 here, I get 1. This is not the problem. This will always be 1 when x approaches 0. The problem is over there, because that is the 0 that is in the way, with the 0 that is in the way from here. But there's nothing I can do. If I rationalize this, nothing is gonna happen. The problem is that top with the 0 from here. So that's the reason we rationalize the numerator. Yes, I know. Normally we rationalize the denominators, but not in this case. So what do we multiply and divide by?
The conjugate.
Exactly, the conjugate of the numerator. Very good. Can anyone give us the conjugate of the numerator?
1 plus.
Excellent.
Square root of 1 plus t.
Yes. So remember, the problem is not this. When t approaches 0, this is just a simple plain 1, which is never going to create a problem. So then, let's multiply the tops. What do we get when we multiply the two tops? Remember, we are using the formula a minus b times a plus b.
1 minus 1 plus t.
Very good. And the denominator now, t, the square root of 1 plus t, in parentheses, 1 plus the square root of 1 plus t. Now, it's very important to understand why we're doing this again. Is it clear why we are rationalizing the numerator? Because this is just a little 1. It's not creating any problem. Okay, so what do you expect to go away? What do you expect to get rid of, I should say better? I expect this t to go away with the t from the top, if the limit exists. Because this is not a problem when I plug in 0. This is not a problem when I plug in 0. This is the only problem. And if I can get it simplified with something like it at the top, then we're in business. If it doesn't go away with something from the top, then the limit may not exist. Ready? So when we simplify the numerator, what will you write? You will write limit as t approaches 0. 1 minus 1 minus t, careful, t, the square root of 1 plus t, 1 plus the square root of 1 plus t. Because we have to distribute, that's why I put it in parentheses, to make sure that we don't forget to distribute negative 1. So obviously these two go away. I would rather write it one more time. I know sometimes we get lazy and we don't, and we simplify it here, but it's not okay. And now you can simplify. This is the culprit. This is the problem. This factor here and here. This is what creates 0 over 0. Not anymore, because we got rid of it. So can anyone give us the final simplified form or the limit? Now, I want to make a point, because I've had situations in the past in which students dropped the limit operator. You cannot drop the limit operator. Look how many times I had to write it. I had to write it at the beginning. I had to write it when I rationalized. I had to write it again when I multiplied. I had to write again when I simplified. And I had to write it the final step. Only now the limit operator disappears when I replace t by 0, because 0 now is in the domain of this new function. Then I can plug it in. Do not, so make yourself a note. Do not drop the limit operator till the final step when you plug in the number. Just in case, go back and put it in if you dropped it by mistake. So I'm going to write this note. Do not drop the limit. It makes no sense if you do. So look, if I omit the limit operator here and here, it makes no sense. This limit is not this. No, it's the limit of this. And it's the limit of this. Okay, so please be careful. Do not drop the limit operator until you are ready to plug in the number. Until we are ready to plug in the number, or plug in A. We are ready to plug in A. In this case, 0. So now coming back to our final problem, final answer, what is it? The numerator is 1, very good. And the denominator, this is 1, and this is 2, very good. So the final simplified form is -1/2. Any questions on this? Please.
2 questions towards the end. One, why is it negative?
-1, -t.
So even though they, because it's negative t, so it'd be negative.
That's
1.
why I have to distribute. Yes?
And how is the bottom 2?
So when this is 0, 1 plus 0 is 1, the square root of 1 is 1. 1 plus 0, the square root of 1 is 1. 1 plus 1 is 2. And that's how we get 2.
Oh, because we're plugging in A.
We're plugging in A, which is 0 in this case. Exactly. Thank you. Yes. Any questions?